So welcome to everyone joining now, little by little. So we'll start in 1 minute when everyone is in. Welcome, Diana.
مشكلة محمد ندخل وقيلة هنايا والله ندخل.
And obviously we have to make sure while we enter to mute the microphone, at least at the beginning till the debate, where then obviously everyone can intervene, but obviously one at a time. So we hopefully have a lively discussion. So you have the title here of the session, of this informal session. Probably they will tell me when everyone is in. If you don't stop me, I think we start now. Again, welcome to everyone. Thanks for joining in this unusual way to do an informal session for eceee. So we have a session on energy and comfort assessment in buildings, where we try to summarize new advances, recent advances, research that have been introduced also in international standards. And this, in our view, can have important implications for policies in Europe and I will unscreen and let the screen to Diana Urge-Vorsatz. She is vice chair of a working group of IPCC and professor at Central European University, or she will correct me if I'm not perfect in introducing her. So I'm glad that she can introduce this discussion. She's working on buildings and low energy buildings since a lot of time, and we welcome her contribution. I unshare, I think I can do this, and if she has slides or okay, I'm not sure I'm doing things correctly. Yeah, I see slides now, and maybe I mute myself and I let the floor to Diana.
Thank you, Lorenzo, and thank you for the invitation. It's a real honor. And if people don't know, but I think we have a long history with Lorenzo for eceee attendance. And for a long time, Lorenzo was one of the few ones who has attended all eceee conferences. I'm not sure if it's so since then. Unfortunately, since my involvement in IPCC, I had less and less time, and I have missed the last couple of ones. But anyway, since it's not possible virtual, I'm here, and thank you for this invitation, Lorenzo. So let me just give you a couple of pieces of background for your informal session. First of all, from the IPCC's perspective and the global helicopter perspective on advances, as Lorenzo mentioned, you're really trying to collect the advances and or review the analysis, and that's exactly what I have done. End of last year, I have published a review paper, which reviewed both the professional and the scientific literature on the advances of net zero buildings. But first, let's jump in to what the IPCC perspective, and what you see here is the famous report of the IPCC on global warming of 1.5 degrees. And what this shows are the different pathways, how we can get still to 1.5 degrees, although many of these are increasingly questionable. But the point is that at that point, there were still many pathways that could lead us to halting climate change at that point. And out of this, I want to zoom in on two particular ones. So each line in this spaghetti is one emission future. I want you to focus on P1 and P4, but first let's zoom in on P4, what this actually looks like. If we decompose it, what does it look like? Now, P4, if we decompose it, the gray is the fossil energy related emissions. Orange is the agriculture, forestry, and land use related emissions, and the yellow is BECCS, so bioenergy combined carbon capture and storage. And the problem is that there is this major concern in the scientific literature recently with all this literature and all these scenarios so heavily relying on bags, because bags has first of all issues with biodiversity, so ecological concerns, but also with costs and many other issues. But if nothing else, just look at the intergenerational justice issue. Basically what this means that we still here continue to have fun while we delegate all these costs to our children, because these have nothing else but costs, because these are going to be very costly to capture carbon dioxide from the atmosphere and store it permanently. That doesn't really have much else to offer. As opposed to that, so scientists were asking, okay, then can we do something else? Not to use so much bags. And yes, the alternative, there are alternatives, but not many scenarios out there which do meet still the stringent climate conditions without this enormous amount of bags. But definitely what you see is the big difference between the two is this basically free fall in energy demand, not only emissions, but energy demand. So meaning that we cannot meet stringent climate goals without controversial technologies, unless with a very strict and very high attention to efficiency and to energy demand decrease. And we know that buildings, and especially heating and cooling in the EU, is key to this, since half of our final energy use in the EU is for heating and cooling. So this is the paper I was talking about. So in this paper in annual reviews last year, we have reviewed all the major scientific literature and also professional literature on net zero buildings. And it was very encouraging, because basically we found that these things, what you see here is actually more a power plant rather than a building. It's the power plant of the 21st century. And this there is plenty of this around the world. This happens to be from China, because I was invited to the keynote and at the Chinese Passivhaus conference. And it was really an experience of a lifetime, because this was just one of the many buildings, which were just an exhibition, and there were just such a big choice of net zero or zero energy buildings, or actually energy plus buildings. And actually these were really pleasant, so you couldn't say that that this is a dark hole to move into. And so I just made this photo of the living room, because this is the energy plus building where I would definitely very much enjoy living, and it absolutely doesn't show that we are living in a hole. But certainly we don't have to go to China for this. And this map, and you know that very well, and I don't want to take your time, because there are many net zero buildings also in Europe. As you see, actually the most are in Europe. But if you look around from the scientific and professional literature, we could collect a very large number of buildings from around the world. So basically what we have shown is that there are basically in every climate zone and every region of the world, it is today possible and economically feasible, and with available skills, it is and available skills and materials and technologies, it is possible and feasible to build and retrofit to net zero energy buildings. The only exception what we found, where we have not found yet fully net zero buildings, were hot and humid and were commercial buildings, so office buildings, high-rise commercial buildings, high-rise office buildings in hot and humid climates, where also a lot of the energy demand is actually not necessarily only for cooling, but for dehumidification, and that has a very large energy requirement, and there it's much harder to do than net zero energy buildings. But in all the rest of the world, although unfortunately there are not many examples yet in Africa, but based on similar climates and experiences in similar climates, it's possible that it's feasible. But what we also concluded, that it's also actually cost effective. In fact, unfortunately, it's not very easy to find scientifically valid evidence for this. But for example, this is the figure that we used in the paper. These are the costs for conventional houses, and in the same area, in the same, so it was an area of Philadelphia, and in the same area, same time period, and we found, or well, actually not we, but what the researchers found actually that the passive houses were in fact cheaper than the average conventional house. Of course, there is a huge spread of costs all over the place, but the point is that that on average, you cannot distinguish. So basically, it is so for newly built, you can definitely do in the cost range of new conventional buildings, and where there were studies we found the same. In terms of for retrofits, and this is from actually origin, it's also from our paper, but also originally from the IPCC report of the fifth assessment report. And these are the retrofits. So the cost of conserved energy from retrofits per, so the CC per kilowatt hour saved, and what this shows as a function of energy percentage saved as compared to the baseline. And yes, we also see that based on different types of climates and building types, there are very different costs. But what we see, sorry, I don't know why the line disappears. Anyway, so the point is that that there should be a line. Yeah, it disappears. But anyway, so what we show is that, yes, you can always put a lot, make everything very expensive, especially in construction. If you do major retrofits, often you don't only retrofit energetically, but also you upgrade the facade, you make things nicer, you put different new tiles and stuff like that. So you can make it expensive. But the point is that you can have the lower end of this curve is constant. So you can have competitive cost of conserved energy for an 80–90% energy saving retrofit, as well as 10% energy saving retrofit. And what you see, as I mentioned, this is kind of the power plant of the 21st century. This is the building of the TU Vienna. And this building is also producing more energy than it's conserving. And I have to admit that here I have made one of my biggest scientific mistakes of my life, because originally I was trying to study which world regions and which building types you can do net zero energy buildings and which building types and regions you can't. And it was also helped by Ksenia Petrichenko's dissertation, which she, I believe, did present at eceee. And there we concluded that this building type is where it's impossible, in places where there's not a lot of solar energy, and we are talking about high-rise building and commercial building. Now, fortunately, I wasn't, if you look at the numbers, I wasn't that stupid to say that, because for this particular example, before renovation, it consumed 800 kilowatt hours per square meter per year. A typical new office building in Vienna is about 450 kilowatt hours per year. And however well you look, you cannot do more than about 60 kilowatt hours of photovoltaic energy per year, per square meter per year. So that means that, yes, there is quite a big mismatch between that. So I perhaps wasn't that stupid to say that that this is not possible. But fortunately, there are more stupid people than I am who just go for the crazy, and this is what they have done. This is the typical new office building and energy consumption, and it doesn't matter, this is in German, but the details don't matter. Really, the point is that it's all the different types of electricity used in the building, and what they have done was this. So what they have done is that they have optimized 9,300 components. And they have, as a result of this, they have reduced the building energy demand by 9/10. So they reduced it to 1/10 of the original power demand. And this is not, most of our studies never really dare saying that you can reduce commercial building plug loads by 9/10, by 90%. But this didn't only study that, but they implemented it. This is what has happened. And also we are doing the same now for the CEU's new building complex in Vienna. We are also trying to reduce the energy demand by that much, by 9/10. But this means that there is no silver bullet, but you really have to have a very, very detailed understanding of the energy use of the people, of the buildings, of the component, of the technologies, and only then you are able to achieve this major reduction. So the key point in the paper that we illustrated by this example was, but also provided other evidence for that, that the key to net zero energy buildings is actually the energy efficiency. So bringing down the energy demand of the building users. So not only heating and cooling, but all energy demand in the building. If you bring it down, then you can produce. Then it is much more possible to do net zero energy buildings. So, as a final point is that, but the problem is that since we are not doing this. And there is, for example, now the renovation wave in Europe. There is a lot of money now under the economic stimulus packages for different construction projects, different infrastructure projects, different building projects. But every single building which we are building from today and that we are retrofitting from today to less than a net zero level, it locks us into a higher temperature future. Why? So this is the study that we have done and published in Nature Climate Change, among others, but there are other references here also at the end at the bottom of the slide. But basically we are showing is that if you compare a very ambitious, this is already a very ambitious building energy scenario globally, because it doesn't increase as big business as usual, as compared to a more ambitious, and this is not far not yet the most ambitious, because this is in our older research. We are updating these numbers now, and Shuran presented our new numbers yesterday. So, but still, even based on the much earlier technologies where we could not yet do such good net zero energy buildings, even then we are locking in 80% of 2005 total global building energy use by doing good buildings, because any times we reduce building energy consumption just by 20, 30, even 50%, you're locking in the remaining 30, 40, 50% that could be saved, because then it's going to be too expensive to go back for this. But by 2040, 2050, we will need that reduction potential as well. Now we can still do it. We can still meet climate goals, because now without them, because it's okay to reduce 30, 40%, but when we have to reduce 80, 90% or 100%, we will need that potential, but it's going to be extremely expensive or impossible to go back for that. So really, it's crucial that from today, every new building that we build, or every building that we renovate, it tends to be net zero. And we have shown that this is all cost effective, and this is not rocket science and available everywhere. So let's not let good crisis go to waste. Thank you for your attention.
My microphone. Thank you very much, Diana. Beautiful introduction. We needed this information, these details, and this energy. So we try now to go on. We have very tight, short presentation. So thank you very much for. And I don't know if you can stay for the entire session since you had another, but we hope you can. Now I try to share my screen and my presentation, and we go immediately to the other. PowerPoint, I guess. Share screen, PowerPoint, share. Okay. So within this European project, which is a collaboration between Africa, and I'm very glad that there are many colleagues from Africa connected now. I hope in the debate we can talk, also discuss. So it's a collaboration on bioclimatic for the new century, with all the challenges of this century: climate change, urbanization, and so on. We present here a part on energy, a part on comfort. There is Lorenzo, Silvia, Andrea, and Salvatore who prepared this work. There is a large network which I will not go through. You will see the slides later. In the project from Europe and from Africa, a number of colleagues that I again greet for this meeting. Energy, what we have found recently, and so these high performance or zero energy buildings, the recent research and the standards tell us that the best way to qualify them is with 3 indicators, not just one. There is this net zero energy concept over a year, which has some problems. Diana already indicated how the good way to solve these problems, but I will come back to that. And implications for policy, possibly in our discussion. So we try to, throughout the project and this presentation, to use one language to be able to communicate effectively, and that's the language of the ISO 52000, where there is a common set of terms and definition about energy performance of buildings, which can be seen also online, not only in the standard, not so easily accessible at this site. So all the definitions are there in English and French. And we start with exactly what Diana was saying, reduce demand, and how can we define very well physically this demand. In the standard, this has a name, which is energy need for cooling, for example, which is the heat to be extracted from the thermally conditioned space. Let's imagine this room is the energy we have to extract from the air contained in this room to keep it in a certain temperature condition, or more generally in a certain comfort scenario condition. And obviously this is a physical quantity which depends on how much energy is entering the building, solar gains, internal gains, and how much energy is leaving the building via transmission losses through the walls to the ground. For example, in a hot climate, maybe we want to lose some energy via the ground, or via ventilation at night and so on. And so the difference between these gains and the losses is the remaining energy need for cooling, the energy that we have to extract actively or with some passive device, but anyway, with systems that will extract this energy to keep the temperature or the conditions stable. The same, the energy need for heating, and we insist on these two terms because and so this is the heat to be delivered to this space to keep it at a certain condition of temperature or comfort. And again, it is a difference between, in this case, the losses. Part of these losses are compensated by towards the cold environment in winter. Part of these losses are compensated by solar gains, by internal gains, but part might need to be delivered by a heating system. And this is called the energy need for heating. And this is this red boundary here, the air within the room. Then we have the systems delivering this energy need, maybe a boiler, a storage, a radiator, a solar panel bringing energy there, gas bringing energy to the boiler. So we can, to obtain this energy need for heating, we use what is called delivered energy, which goes to the meter. Well, it can be energy coming from the renewable energy at the site or from the grid. The total entering the building, the systems of the building, is called delivered energy. And then we finally have this primary energy where we multiply the delivered energy, it is 18 part fossil and part renewable, by that take down the losses from the source to the boundary of the building. And so we get total primary energy if we consider the sum of all delivered energy, renewable and non-renewable flows, and we multiply each of them for their respective factor, which take account of the losses. If then we consider the non-renewable part of these flows, and we multiply that for taking account the loss into account the losses, then we have what is called non-renewable primary energy. So we have these indicators, and sometimes the buildings are qualified using only one indicator, but that's a very incomplete way. The standard says using only one requirement is misleading, not only insufficient. And we need to have 3 indicators and fulfill each of them. It's a sort of hurdle race where we have to fulfill overcome 3 obstacles, which are the energy need for heating and cooling, which describe the thermal envelope and the heat recovery on ventilation. And these, as Diana was showing, can be highly reduced. This demand for energy can be reduced of 80–90%, for example, the use for heating and cooling in new buildings, in retrofitted buildings. And that's the first hurdle that we overcome, and the biggest one, the one where we can make a difference. Total primary energy describes how the active systems use fossil or renewables efficiently or inefficiently, and this is a low total primary energy, a second step to achieve, and then a low non-renewable primary energy, so a low part of primary energy coming from fossil is the third thing to do. And so we can say the energy efficiency first principle is telling us to make as low as possible the energy needs, first of all, and the total primary energy. And the objective on increasing the share of renewables is achieved if we can reduce the indicator non-renewable energy. Sometimes these objectives are expressed through this net zero energy balance over a year, which can be described as exported renewable primary minus imported primary to the building. So we could say, okay, over a year, we have as much imported from the grid as much as we export of renewables to the grid. These two things balance out, and we have a zero energy use. And this, for example, in this example, that's what we have over a year, which is a good goal. But if we then look hour by hour, or in this case, month by month, we will see that if energy is generated by photovoltaic in Milano, we generate a lot of this green energy in summer and much less in winter, where we need, so we have more use in winter than production, and vice versa, which means that we still burn gas and emit CO2 in winter. And if we do this balance where we say, okay, but the total is zero, we are assuming that the photovoltaic, which I export to the grid in summer, will be available for me in winter for free with no losses due to having been stored for 6 months. This is obviously physically not true. Interseasonal storage costs materials, embodied energy, and energy losses. So we should try to reduce this problem by regulation. For example, the energy balance in Italy is calculated on a monthly basis, not on a yearly basis. So you can't offset your overconsumption of winter with the overproduction of summer. We could calculate the renewable primary energy factor, including the losses, while in a the trivial way to do this balance, the losses are simply ignored. But obviously the big way to do it is physical. If we reduce the energy needs, if we have a very low demand, also the unbalance between hour and 1 hour and the next, and the imbalance between summer and winter will be reduced of a factor 10. So reducing the requirements for storage and transmission infrastructure. There is another issue with this zero energy balance. Here it's a case of a village with well-insulated buildings, heat pumps, PV battery, optimizing it for net zero energy. The researchers find that, okay, the optimization doesn't use the battery at all, because using the battery means having losses of storage. You store, you recover, you don't recover 100%. So in terms of this balance, it's much better to sell to the grid where the losses magically disappear in this accounting. So in this sense, net zero is as an objective, mathematical objective, is in conflict with maximizing the self-use of renewables using storage when, and that's up to Salvatore Carlucci, who is a professor from Cyprus Institute, to come in. I don't know, Salvatore, if you want to share your own screen or tell me if I use this presentation here.
Thank you, Lorenzo. If possible, I share the other.
Okay, so I unshare.
Thank you.
Floor is yours. Thank you for accepting this invitation to share with us also common.
It's a big pleasure. Thank you really much, Lorenzo. Thank you, everybody, for being here this afternoon. So the second part of this chat was about comfort. So what is thermal comfort? There is a general definition that is incorporated into standards since many years now, according to which thermal comfort is that condition of mind that expresses satisfaction with the thermal environment and is assessed by subjective evaluation. This is specifically the version of the ASHRAE 55. But what that means is a quite, let's say, not physically bounded definition. There are terms like satisfaction, like subjective evaluation, how this can really help a physical design of net zero energy buildings. There is a context in which the term of thermal comfort is fitting. That is this kind of schematic where we consider the human body, each of us, exposed to some environmental condition, and what we perceive as a thermal sensation is basically the results of the reaction of our body. This is a physiological adaptation to the environmental condition. And there are some models developed in the past 50 years, basically, that have tried to quantify this effect in order to predict, assess thermal condition in buildings affecting human body. Then there is a second level, it is the thermal perception, how we perceive the thermal environment in which we are. And in this case, we have a second layer, second lens, let's say, to interpret the condition that is due to our psychological reaction and adaptation to it. Then there is another level that is actually the adaptive control that we act in the building. And it depends, of course, on the psychological adaptation that we use, but also behavioral adaptation. So also what we are as a social human beings, this might impact the way in which we interact with the building. But thermal sensation is one, without going too much into the details, thermal sensation is quite interesting since it's something that is quite easy to understand and is directly used for some of the assessment that we will see in a while. It is expressed typically on a 7-point thermal sensation scale. There are also other ways to do it, and basically is a vote that each of us can express in order to qualify what is the thermal environment in which we are in. It is represented using this discrete scale from +3 to -3, hot to cold. There are official translation in other languages, and then the typical English translation, the reference to the English translation is from hot to cold, passing through warm, slightly warm, neutral, slightly cold, cool, and cold. This is the way in which we typically try to evaluate thermal sensation, and this is the way that is used by rational models that are typically energy balance based models that try to model like a white box the human body and try to account for each of the energy fluxes entering and leaving the human body. Just a brief introduction about thermal comfort, the evolution of thermal comfort. Everything started in the 60s, was started framed in the 70s, the models, I mean, and then in the 80s, there was the strengthening of the concept. So one of the most important and referenced models, in particular of this kind of rational approach, energy balance based, is the Fanger model, also called the PMV-PPD model, where PMV stands for predicting mean value, and the PPD for predicted percentage of dissatisfied people. It's a model that gets as an input 6 variables, but none of them is related with the outdoor climate. That was one of the first criticisms that this model got. But this model was really accepted by the community and has been integrated into standards, still referred until now. It was very important to mention now that Fanger in the 70s, in the book Thermal Comfort in the 70s, mentioned that humidity has a low influence on thermal comfort. This is something that is extremely important to keep in mind also for assessment that we will discuss later. And one important element is that when Fanger presented the model, he stated that the model is reliable, can be used for considering some ranges for the input variables, and relatively to the relative humidity, these ranges from 30 to 70. So outside this range, this model should not be applied. This became something different, possibly with the time, considered like a sort of range where the model fits or comfort condition might be expressed. No, it's something different. This is a scope of the model. The second, meanwhile, in the same period, Humphrey and Nichol proposed another approach, an adaptive comfort model that takes into account the 3 layers that we discussed just previously, and they come out with a nonlinear regression model, a linear regression model that basically gets one variable as an input that is representing in some way the outdoor climate. It is called running mean outdoor temperature. It is an exponential decay elaborate function or based on the outdoor temperature, ambient temperature. And if we want to simplify it, is basically the average temperature of the last 7 days, more or less. There is a third approach that was very common in that period in the 80s, proposed by Baruch Givoni and Ed Arens, that was also represented graphically through bioclimatic chart, where it was very interesting to see that air velocity played a very important role, while humidity again was there but was not really changing the game. This is just a picture of these 2 graphs where you can see the comfort zone. I hope you can see my pointer. This is one comfort zone. This is an extended comfort zone for the increased air speed, and this is the other one where we have the comfort zone. As you see, we go from 95% up to basically 4 grams per kilogram of dry air, and other strategies to bring in while expanding, increasing the velocity. You can see how the comfort zone gets expanded. Now, oops. Oh. It's also interesting to mention that always Arens, we are in the 90s here, mentioned something like for natural cooling, it was necessary to modify the upper humidity level given in the ASHRAE standard. This is in 1981. And this is a number that in our community is quite common, is 12 grams of vapor for a kilogram of dry air. And the justification of it was that this value is based on avoiding condensation and mild growth in the ducts of centrally air-conditioned building, rather than on human thermal comfort requirements. So again, this kind of threshold was present in order to solve a very important technical issue, and was in some ways extrapolated and used like a sort of threshold for thermal comfort application. That is not the case. Then the engineering practice in the last decades have in some ways incorporated, and this is very good, thermal comfort models, sometimes approximating, simplifying them in a way that actually is not really aligned and comparable with the original indications of the main researchers. So, for example, this is a picture from a standard. What we can see for a specific, without getting too much into the details, what we see here are the temperature range for the heating season and for the cooling season, where the typical conditions for energy calculations are presented with this range. For heating is from 20 to 24, and for cooling from 23 to 26, giving the possibility to the energy analyst to decide what kind of threshold. So we could also get into the paradox of choosing 23 degrees like set point for cooling, while the set point for heating might be 24. That is quite crazy, but actually Ed Arens, again, through an experimental campaign in California, demonstrated that in average, these are the kind of figures that are identified. Why? Sometimes we, as practitioners, we mess up between design, control, assessment. These are completely different aspects that require a different hypothesis and sometimes different assumptions. This is extremely important to keep also in mind. Going closer to our time, we are at 21st century. So also Fanger in 2002 acknowledged that his model might suffer low predictive skills in real building, basically due to the fact that this model was developed in climate chambers, in laboratory studies, in particular in warm climates. And there was he proposed the corrective factors that applied could even expand the comfort range by a factor of 2. So you see how big start becoming the sort of uncertainty applied here. Meanwhile, in the latest year, thanks to some attempt like the European SCAT projects, the ASHRAE P884, and that brought to the creation of the first ASHRAE Global Thermal Comfort Database #1, adaptive models were introduced. First, integrated into the ASHRAE 55 in 2004, and then also we had the European one integrated into standard in 2007. Recently, thanks to the contribution of all the community of thermal comfort and some annexes like the Annex 69, a new ASHRAE Global Thermal Comfort Database has been released, incorporating even more data than before, and represents the largest data source available on thermal comfort in the world, covering different type of buildings, thermal zones, different conditions. What is interesting is that also standards evolved along the time, and basically the EN 15251 that incorporated first the European adaptive comfort model has been superseded by the EN 16798 part 1 2019, and also the ASHRAE 55 is in this kind of ongoing, we will speak about that, ongoing revision process, but both of them confirmed the validity of the adaptive hypothesis, since it's still there, actually is getting strengthened. Just to give you an overview, so the first time that the thermal comfort got integrated as a concept in standard, technical standard, happened in 1966 with ASHRAE 55. And the latest revision of this set of standards on thermal comfort is in 2020. So it's what, about 50 years that we are discussing about thermal comfort. Here you can see in red the evolution of the ASHRAE 55. We see that there was a first revision 74 in 81, I mentioned this earlier, then 92. And since 2004, the adaptive comfort model has been integrated, and since then is in this kind of continuous revision process. Every 3 to 5 years, this standard is updated with the latest advancement and evidences from the research. Here we see also the ISO standard that right now incorporates just the Fanger comfort model. Has been, the latest version is of 2005 and was revised but with confirmation 2015. And then the European efforts with the EN 15251 2007 revised in 2019, where we both have the Fanger comfort model and the European adaptive model. So there is a lot of activity in this sense. Now, just to summarize a few key points that might be helpful for this discussion, we will refer to the latest version, the most updated one, that is the ASHRAE 55 to version 2020, that has some very important elements of novelty in its latest revision. Just picking some elements, there are even more novelties, but basically, the first element is that the applicability of the adaptive comfort model has been extended also to buildings that have mechanical cooling systems installed, as long as they are not in operation. Before, it was just the adaptive comfort model was just limited to naturally ventilated buildings. They were called in that way. Also, what is interesting, the second point here, is that the operating set point for buildings are not mandates. So there is not a table that says this is the reference value by this standard. So we are moving towards what will be the latest point. Instead of specifying specific conditions, we can specify scenarios that the designer can meet, and this can give flexibility to adapt to specific condition, site specific or occupant specific condition. Extremely important new element, the third point here, air velocity has been integrated, formally integrated, both modifying an analytic model with the introduction of this elevated airspeed comfort zone method that is based on PMV plus the set standard effective temperature that is applied to when the airspeed is higher than 0.2 meters per second. And then it's also in some ways integrated, added to the adaptive comfort model. We will see that in a show. There is the confirmation of the low influence of humidity on thermal comfort perceived by people. And we have a tool. Now, we have no anymore tables or graphs that represent pictures, but we have a tool that can be used by designers in order to test hypothesis solutions and to make a more informed and substantiate design. So this is the latest point that is extremely interesting here. So we have not anymore the 21, 24 degree C scenario, but condition set points, but we have comfort scenario. So we set the condition. Oops. This is just the analytical comfort zone method based on the PMV PPD, so the Fanger comfort model that is represented in normative appendix B. We have compliance with the model if the PMV predicted mean vote fall within this range between minus plus and 0.5. The tool, this thermal comfort tool, can model all these, includes and cover all these models. And what we have to keep in mind, when we want to apply this model, we have to consider that the metabolic rate of occupants has to be between 1 and 2 MET, and the average airspeed has to be lower than 0.2. Then this model will ask for some additional verification that based on local thermal discomforts. And what we see is that we have no upper and lower limits on relative humidity. So this is a difference with respect even with the bioclimatic charts of Givoni and Arens that were 95% and something about here, 0.04. Then we have also not anymore, this reference to the 12 grams of water per kilo of dry air. So actually we move up to saturation. Elevated airspeed comfort zone method is an analytical tool that is based coupling the PMV plus the set and basically provide additional information on the thermal comfort zone for airspeed that is higher than this 0.2. And actually what is really interesting is that we could be in comfort for sets that might reach even temperatures that are in the range of 30, 31 degrees with airspeed that are in the order of 1.2 meter per second. This is extremely important. This changes the way in which we deal with comfort in this case. And also here, we should also consider whether we have or not the capacity of controlling the airspeed. In order to achieve this condition, we need to provide users the possibility to directly control them. Now, I would like to challenge you to look this and compare this with the previous table. It's very much different, the kind of condition that we can represent.
So, Dottore, just they are telling me that we are till 4:15, so we need to leave some space for some discussion. But
okay, I'll go to conclusion.
Thank you very much. Very clear. I'm
in a few minutes. What that means, that kind of ASP, basically installing, for example, these kind of ceiling fans can be very effective in increasing airspeed. There are tools, again, that can help us in designing these solutions. Then, the elevated airspeed, basically you see here what is the impact from moving from 0.1 meter per second to 0.5, that is not extreme airspeed. We have an increase, a shift of the comfort range by at least 3 degrees. Again, the influence of humidity is quite small. It's just the slope of this line that is here presented. The adaptive model. Here, the input is the prevailing mean outdoor air temperature. Then we get the optimal condition. And what is really important is that now we could consider under the scope of this standard also buildings that have mechanically cooling and heating systems, but they are not in operation, that specific model. But the people have to be free to adapt their clothing, so no dress clothes or things like that. Another important change is in the reference comfort conditions, that now is the 80% acceptability class, while the 90% that we bring from the past is now just for information purposes, and in case of higher standard of thermal comfort is desired, even if in the literature this is not always the case. And other important elements too, local thermal discomfort, clothing insulation, metabolic rate, and humidity and airspeed are in this case already included into the model. But the novelty is that for operative temperatures that are higher than 25 degrees, we can add a correction factor. We can expand the upper acceptability temperature by some degrees according to the velocity that we bring here. 0.6 expand by 1.2 up to 2.2 degrees for 1.2 meter per second airspeed. And then please, Lorenzo, if you want to take the...
I'm thinking of skipping these examples. So these are examples of use of the tool. It's really a very good tool that the university group has generated. As colleagues with which we are working we have been working for the database, etc. They are doing very good work on this. Maybe you go on, Salvatore, just at the next one. And so we see, for example, the velocity correction applied to the adaptive, which brings in comfort what was previously out of comfort, this 27 point and degree Celsius condition. Go on. And increasing air velocity, the comfort zone expands towards the higher temperatures. And you see directly how the comfort zone changes by changing air velocity and your condition fits into the comfort zone. I think we have a final slide on a case where we have a Passivhaus in Sicily, and we see that this house with very low energy needs, with very good envelope, with high insulation, solar protection, and so on, is able to passively maintain indoor conditions, the operative temperature indoor, into the comfort zone prescribed by the adaptive model, even with this high temperature 38 and so on. There is a lot to do, and today is introduction to see how these concepts and this special, this clear language that the standards offer, this clear description of comfort now can possibly be used in our search for good solutions with the colleagues from many countries, from Africa, from Europe, within the project, but also how to intervene so that this clarity that we have now available can be incorporated into the policy documents that are under preparation in Europe and in Africa. That's, Adrian, would you like to say something about this? Or, and others?
Yeah, thank you, Lorenzo. I know you invited me to make some comments here. Delighted to take the floor. However, of course, this is highly technical, and the thoughts crossing my mind as I listened were, why does a higher velocity make it possible to go to a higher temperature? And is that because of evaporative cooling from the surface of our body, where our own sweat or humidity is being evaporated more quickly, so we can cope better with the higher temperature? But the second thought I was having was about EU policy. To what impact can this research and this work, which is, yeah, as you said, it's a rationally based system, can it be reflected in policy decisions coming up with the revision of the Buildings Directive, for example? And I rather fear that it would be very difficult to incorporate this at this time because of the scientific complexity of what you're putting forward, and policymakers who don't, understand those subtleties, trying to be diplomatic, and won't necessarily see its relevance to how it can impact on the indicators of the way we describe highly energy efficient buildings. But on a more general note, so working back towards Diana's scene setting, it is true that there's a lot of push for including more indicators and more metrics, is what I tend to call them, for describing energy performance in buildings, in order to bring more to the surface these additional benefits. Like we are always saying that highly energy efficient buildings are more comfortable and more healthy buildings. And if this work can show that more dynamically, then I think we're going to get closer to a circumstance where these advances in how we understand thermal comfort can be reflected in policy. So I understand time is really tight, Lorenzo. This is why I've been rushing a bit in my comments. But these are the thoughts that have been crossing my mind as I listened to you. And I suppose to end on Diana's scene setting, her call that all new buildings be net zero is also something that can be considered in the Buildings Directive, because a number of voices are calling for the definition of nearly zero energy buildings to be upgraded to something like what Diana called for. And that would mean that all new buildings from a certain date in the near future would be required to be that level of performance within the European Union. So I hope they're helpful reflections, Lorenzo, and maybe there are others in the audience. I see some colleagues are in the audience that might wish to also make a comment. So Lorenzo, I'll stop there for the moment.
Thanks. Thank you very much, Adrian. I would just comment again. Let's try, if it's possible, to set up, I don't know, a working group to further reflect on this and see, okay, if net zero is really a good definition, or if we need those three indicators define zero energy in a much more comprehensive way. But that's I see maybe that Nelson wants to intervene, and he might add to this discussion, certainly. Please. And thanks, Adrian, for the moment, obviously. Nelson, would you like to turn on your microphone? You are asking to intervene, right?
Okay.
Please.
Hello. So when I read your PDF, can you listen? Can you listen?
Yeah, not.
When I read your PDF, I was really scared because I thought you might be wondering about exporting the Portuguese energy performance certification process to Africa, and that would be horrible because it's so many simplifications that have absolutely nothing to do with science. It's like your house has got a consumption of the number of your rooms plus something. I presented a paper on Monday. But now I see that the idea is to use real building physics, which is nice. It should be important. I would just adapt to your idea of good science, not simplification. The idea of scale, neighborhood scale, because in Europe, we are working stupidly individually, and it makes absolutely no sense because in a neighborhood, all the buildings are more or less the same. And so if you make an intervention on one building, then the learning curve for who's doing the intervention is a lot more interesting. Then you can put in interdisciplinary teams and the cost can go a lot lower. I made a presentation on that on Monday morning on policy. But I would really like to continue following up. We should have a group to discuss these things. Okay, sorry for the bad conditions. I'm in the south of Portugal, not in the south of France.
Thank you for your contribution. And let's see, obviously the idea is to see if we can expand this network that is trying not to export anything, but to work together to understand what can be good in the various situations. And je ne sais pas si aussi les collègues de l'Afrique préfèrent de parler en français au lieu d'anglais, et on peut faire une petite traduction si c'est plus facile pour intervenir. Et je vois des collègues qui j'aimerais bien avoir leur opinion ou même aussi seulement se présenter si vous voulez. Ce travail d'interaction, c'est un travail qui pourrait avoir, on espère, un grand potentiel de mettre en commun les expériences magnifiques qui sont en train de se passer dans certains pays, notamment en Afrique, de construction de bâtiments passifs qui exploitent bien la physique et le climat du lieu et les matériaux du lieu. On a Asma qui est en train de travailler sur les matériaux geo-sourced and bio-sourced and so on. We will have specific workshops on materials and other workshops another workshop on policy, a workshop on future weather files to take into account the evolution of weather for the future. Alors, je ne sais pas, c'est une invitation si quelqu'un autre de l'Afrique ou de la Réunion veut intervenir. Sinon, on peut demander encore, je ne sais pas, Céline ou Adrian, si on reste en Europe, qu'est-ce qu'on peut faire sur la question de la révision de la directive maintenant, on the Building Directive revision. I think it would be really good if we could continue what we did already last time to try to bring into the debate the best available knowledge, which now is synthesized in part of the standards, not all, but maybe someone
Hello.
or others.
Hello.
Please.
Okay.
Oui.
Si Lorenzo le permet, je vais y aller en français.
Oui, très bien, merci.
Ok, alors moi c'est Komla Delagake de Léamo, situé au Togo. Alors,
Dis-nous,
déjà à ceux qui ont fait les présentations. Alors, du coup, sur le concept, je crois que ça va, le message, il est clair. Mais ici en Afrique, le gros problème, c'est qu'il va falloir faire de grosses campagnes de communication pour que ce ne soit pas juste un simple slogan. Je m'explique. Alors, au niveau des habitudes ici, alors, nous n'avons pas, un, la maîtrise des matériaux. Deux, ce qu'on a comme dogme ou comme culture a été transformé au fil du temps dû aux influences externes. Ce qui fait que les matériaux dits passifs ont été longtemps présentés comme étant des matériaux pour des logements sociaux, enfin, des matériaux de pauvres. Donc, la plupart de ceux qui ont les moyens construisent, mais ne construisent pas avec ces matériaux parce qu'ils l'assimilent à des matériaux qui sont utilisés par les pauvres. Et quand ils veulent réussir, alors, une des façons de montrer leur réussite, c'est à travers leur maison, leur habitat, et ils n'aiment pas construire dans ces matériaux. Donc, du coup, alors les gens entendent, oui, construction bioclimatique, construction passive, tout le monde est d'accord, mais personne ne veut l'appliquer parce qu'ils ne s'identifient pas à ce genre de construction. Alors, moi, je donne l'exemple, par exemple, d'un client qui a entendu parler d'architecture bioclimatique, de matériaux locaux, qui voulait s'y mettre, et il est d'accord. Alors, on a fini le projet et paf, la première des choses qu'il me dit, par exemple, pour son lit, il veut un lit avec une grosse couette, comme ça se fait dans les hôtels en Europe. Alors, pour dormir dans un climat chaud, dans un lit avec une couette, il va falloir climatiser. Donc, ça ne le dérangeait pas de climatiser. Et lui, ta maison, oui.
Ok, donc alors, je vais te faire une traduction parce que pour moi, couette, c'est une couverture très épaisse sur le lit.
Exactement, oui.
Donc, le client voulait dormir sous une grande couverture. So maybe for those not speaking French, what our colleague is saying is that there is also an issue of attitude of the clients, those who ask for a building that are now influenced by the Occidental way to construct and consider the original materials, the local materials, the raw earth, the insulation made with fibers as poor materials and materials for the poor, even if they have very good properties and could deliver very good buildings, and also other anecdotal experiences like in a hotel willing to sleep with a big, what would be the name in English for, maybe Adrian can help.
A quilt, a big quilt.
A big quilt, something very heavy. And so then you need to have air conditioning to reduce the, so there are, we know also here that we have taken strange attitudes. Please go on. I just made the translation of quit.
Non, c'est ça. Alors maintenant, ça c'est au niveau de l'individu. Quand on passe à l'échelle du quartier ou de la ville, par exemple, alors moi je prendrais l'exemple tout simple de la ville de Lomé qui actuellement est en construction. C'est-à-dire un certain nombre d'infrastructures sont en train d'être faites, notamment la voirie. Alors moi, la grande voie qui passe devant moi, qu'est-ce qui s'est passé? C'était une voie qui était arborée. Alors du coup, dès que les engins sont passés, ils ont coupé tous les arbres, ils ont mis du bitume sur une emprise de 70 mètres. Et dans ce qu'ils sont en train de faire, il n'y a aucun plan pour sauvegarder les arbres, ça c'est déjà coupé, ni aucun plan pour en replanter de nouveau. Alors on nous dit d'être passif, de marcher, de privilégier la marche aux voitures par exemple. Alors on nous coupe les arbres avec un soleil qui est en plein midi, qui tape dans les 35 degrés, qui va marcher alors dans la rue, qui va prendre sa voiture. Ça, au niveau même de la politique nationale, je crois que les gens le prennent comme étant un slogan, mais tout le monde court vers un soi-disant développement qui n'est en réalité que du fétif, qui va nous conduire lamentablement là où on ne veut pas. Pour maintenant, au niveau du troisième exemple que je vais donner, c'est ça, je le donne pour piquer un peu les uns les autres, c'est au niveau de nos habitudes vestimentaires. Alors, les habitudes vestimentaires ici, alors c'est de sortir sous le chaud soleil, climat humide, en costume cravate. Donc, ça nous fait 3 peaux en plus de notre peau initiale. Ce qui fait que quand on va au service, c'est la climatisation qui est à fond. Alors, tout à l'heure, on a défini la notion de confort, alors qui est très subjective. Alors, les gens pensent que le confort ici, c'est de mettre la climatisation à fond et d'avoir une température tempérée comme en Europe. Et quand on met son costume cravate pour aller le faire, mais vous imaginez que tous les climatiseurs tournent et quand on met l'ensemble des climatiseurs qui tournent, qui rejettent de la chaleur, donc quand ça crée un système où les gens vont utiliser plus de climatiseurs parce que rejetant la chaleur sur l'autre, l'autre aussi va augmenter et ça s'amplifie.
Oui, oui, je vois le problème. Peut-être Adrien veut faire un commentaire sur ça ou quelqu'un autre. Donc, je traduis en anglais juste en seconde. OK, il y a there are personal attitudes and also the policy of not keeping the street comfortable by taking away trees and also other personal attitudes of wearing a suit and so heavy dress and then the air conditioning. So I agree with you. That's not happening. It's happening in a number of places, and that's well partly what these comfort studies want to disprove, that this is the way to achieve real comfort. Comments, please.
Lorenzo, I see Mansour, So, and Regis Meyer want the floor.
Regis, yeah, sure.
So Mansour, maybe first.
Mansour was
ouais,
first.
Bonjour,
oui,
moi aussi,
français.
je vais parler français. Je suis au Sénégal, donc voilà, donc je remercie déjà Comlan hein, qui a déjà parlé pour le Togo, mais il a parlé pour le Sénégal aussi, parce que c'est les mêmes réalités et nous vivons à peu près les mêmes choses, donc je ne vais pas revenir là-dessus. Par contre, je voulais un peu poser la question sur le système Fangère, donc sur le système PMV-PPD. On a bien suivi que c'était possible de l'utiliser dans un bâtiment où il y a de la climatisation artificielle, si, par exemple, ces appareils étaient à l'arrêt. Maintenant, le problème qui se posera peut-être, c'est que si on part déjà, a priori, au niveau conception, de faire un bâtiment climatisé, c'est pas du tout la même chose, c'est pas du tout la même approche qu'un bâtiment qui est naturellement ventilé. Alors, si on fait par exemple cette conception de bâtiment climatisé avec l'étanchéité et tout ce qu'il faut, est-ce que cette méthode-là pourra être utilisée en arrêtant la climatisation et ensuite pouvoir dire que c'est applicable comme si on avait un bâtiment qui avait une ventilation naturelle. Donc ça, c'est quelque chose qu'il faudra que... Je suis en train de me poser cette question-là depuis un certain temps, parce que j'ai fait un peu quelques études, quelques enquêtes de confort ici au niveau du Sénégal. Bon, au niveau de la conception ici, presque, on peut faire des catégories, hein. Il y a des gens qui construisent parce que pour eux, c'est tout simplement, il va falloir climatiser. Donc, toute la conception est basée sur donc, la résolution du problème de confort par la climatisation. Donc, d'autres personnes qui n'ont pas les moyens vont construire pour faire de la ventilation naturelle. Alors, donc, il faudra qu'on trouve un terrain intermédiaire, un bâtiment qui peut être donc un peu ambivalent, qui peut être ventilé quand on n'a vraiment pas besoin de faire de la climatisation, mais avec efficacité quand on doit faire de la ventilation, de la climatisation sans avoir beaucoup de pertes, comme vous avez décrit tout à l'heure au début. Voilà. Donc, c'est juste ce que je voulais dire. Dire aussi que j'ai travaillé un peu dans le projet TIFA, donc qui avait comme objectif donc de valoriser un réseau qui est au Sénégal comme isolant thermique au niveau donc des bâtiments. Et je suis en train moi-même de faire des expériences chez moi en utilisant ce matériau-là pour voir un peu l'impact que ça peut faire donc, dans une habitation au niveau atténuation de la température, au niveau des phasages, etc. Voilà, donc je suis vraiment très heureux de rejoindre ce groupe-là. Je sais que je vais apprendre beaucoup de choses. Alors, je vous remercie beaucoup.
Réciproquement. Nous, on a besoin d'apprendre pour l'utilisation de ce matériau, on a besoin d'apprendre les conditions locales. C'est un groupe de travail. Donc, I just translate quickly and then I give the word to Regis for final comment, and then I guess we have to close because the platform probably will close. So yes, the point was adapting this concept of comfort and the possibility to use adaptive comfort in buildings which have a mechanical cooling. Would this, let's say, impact negatively on the design? And that's a very good question. I guess not, but again, this issue of buildings that can be naturally ventilated at times and mechanically cooled at other times, how we design for these conditions, extreme conditions in Africa is a extremely relevant, important question. I hope we can, during the rest of the project, exchange on this particularly. And on the materials, certainly the local materials. Regis, please. And thanks for the comment.
Oui, bonjour à tous, je vais parler en français. D'abord, merci d'organiser cette première conférence en ligne très intéressante. J'avais plusieurs commentaires. Vous connaissez la pondération des profils énergétiques qui se passe en Californie. Il s'appelle Time Dependent Valuation, qui essaie de mettre en gros, c'est une approche par coût, qui essaie de minimiser finalement le coût énergétique en prenant le coût de production du réseau. Mais en fait, on peut très bien imaginer un poids écologique, en gros, en quelque sorte. C'est pour résoudre le problème de la balance annuelle, quoi. Voilà, donc ça, c'est une première remarque. Deuxième remarque, c'est l'aspect du confort. Ça me laisse à supposer que quel type de formation et que ça nécessiterait un effort de formation particulier si une réglementation passait avec un concept que vous proposez, quoi. Enfin, quel est l'impact de prendre ce genre de proposition? Et le deuxième, peut-être dernier commentaire, c'était pour dire en France, sur la très bonne question de notre collègue du Sénégal, en France, on a essayé dans la réglementation 2020 justement d'avoir une réponse sur cet aspect, d'inciter le plus possible à des bâtiments sans climatisation, mais en incitant, s'il y a une climatisation, que ce soit performante, quoi. Voilà. Donc, ce serait intéressant peut-être de se mettre en relation pour expliquer un peu comment on a fait cette approche en France, qui est une tentative de réponse. Voilà, merci.
On va avoir, we'll have specific sessions also on this. So Regis, who has been one of the initiator of this project, be the initiator of this project and pushing us to cooperate for this, we will try to answer some of these questions working together again. Adrian has a comment probably.
Oui, merci Lorenzo. Je voulais juste commenter ce qu'il a dit Mansour, parce que c'est très sensé ce qu'il a dit. Il a dit que la conception du bâtiment est fondamentale à la bonne opération et la basse consommation du bâtiment. Et moi, je trouve difficile à voir comment on peut avoir un bâtiment qui va bien fonctionner dans les deux modes, même si le climat ou le météo change à l'extérieur. Et en plus, de bâtir un tel bâtiment coûte plus cher parce que tu dois répondre avec deux systèmes au lieu d'avoir un système bien conçu au départ, soit mécanique, soit naturel ou bioclimatique. Et de toute façon, à mon sens, d'avoir un bâtiment plutôt bioclimatique où la demande d'énergie est moindre et toujours plus sensé qu'un bâtiment où on a une demande d'énergie pour toutes les années à venir pendant le vide du bâtiment. Alors, je voulais juste faire ce commentaire sur ce qu'il a dit Mansour. Et j'ai tout à fait reconnu les problèmes dont lui et notre collègue de le Gabon a dit sur l'association qu'on fait avec les matériaux qui étaient dans le passé les matériaux traditionnels et maintenant associés avec les pauvres et que c'est très difficile de passer ces matériaux dans un monde moderne. Voilà, mais de participer dans le groupe, oui, ça m'intéresse évidemment. Et de réfléchir plus précisément comment on peut avoir un impact sur les réglementations et les législations au niveau européen. Oui, ça c'est très, très intéressant de voir ça ensemble. Voilà, merci.
Okay. Merci Adrien, merci à tous vraiment. Et on va... on va avoir aussi une discussion sur les politiques en Europe et en Afrique où il y a des procédures de préparation de nouvelles réglementations où il va avoir des intérêts à interagir avec le groupe. Bien sûr, on n'a rien à... disons, on n'a pas de solution déjà préparée, on a seulement une grande curiosité, un grand intérêt à travailler ensemble et trouver les bonnes solutions qui sont là. La physique est là, on peut les trouver, mais il faut du travail. Et donc, voilà, c'est un premier essai aujourd'hui de réunir un peu plus de gens autour des premiers résultats du projet et on va sûrement vous informer. Maintenant, on a au moins de ce groupe-là, on a les mails, les références et on va vous informer sur le prochain webinaire et sur la publication des premiers rapports qu'on est en train de produire, de finaliser. Sylvia qui est là, Andrea, Alessandra, Salvatore aussi, il a contribué avec les discussions et on va le mettre à disposition. Et bien sûr, on est très content de recevoir des commentaires, des critiques. Et je crois que s'il y a encore quelqu'un qui veut parler, bienvenue, mais j'imagine qu'on doit... qu'on doit probablement clôturer le meeting. Je ne sais pas, Camilla.
Yes, I think we...
On est moins déjà. We are a smaller group now, and probably we have to finish because there are probably others going on in the conference, right?
Yes, yes. So, of course, we are going to have more webinars related to different topics of the project. So I do invite everyone to access our website. Suzanne has written in the chat. And I will also keep your contacts to keep you posted of our results and next events. As you can see, we have a very broad project between Africa and Europe, and very interesting reports are coming out soon, so keep posted. And I think that's it. That would be the wrap up.
Okay. Thank you very much. Thank you for all for the intervention, for the contacts that I see in the chat, and I see Ernest. Je vois Ernest aussi. Bon, je ne peux pas faire des salutations à tout le monde directement, mais merci beaucoup. J'espère que ça a été un peu intéressant et qu'on peut se retrouver et continuer la discussion comme l'un et tous les autres. Merci, Virginie, tout le monde. Fabrice.
Oui.
Au revoir.
Merci à tous, au revoir.
On va se retrouver un jour
Merci, au revoir.
En personne, peut-être.
Merci, thank you very
Au revoir.
much.
Silvia,
Bye.
Silvia,
Thank
Alessandro.
you.
Domenico.
Bye, everyone.
Grazie.
Bye.
Thank you, bye.